Figure 7 shows a tuning fork. When the prongs of the tuning fork are struck, the prongs vibrate in the direction shown by the arrows in Figure 7. Describe how the vibrating tuning fork causes a sound wave to travel through the air. You may add to the diagram if it helps your answer. So basically what this will cause is vibrations that travel, or the particles which are vibrating in the air will vibrate back and forth and basically create a longitudinal wave. So they'll vibrate back and forth, knocking into each other, creating rarefactions and compressions. So if you remember, a longitudinal wave is when, as the wave travels forward, it causes particles to vibrate back and forth longitudinally, and that's what you have to get across. So the prong makes the air vibrate, or the air particles vibrate, in the same direction as the wave travels. So you could express that in a number of ways. So you could say the particles vibrate back and forth, or they vibrate in the same direction as the wave is traveling. As opposed to a light wave, which causes particles to oscillate at 90 degrees to the direction of wave travel. So that's a transverse wave, as opposed to a longitudinal wave, that's sound. Okay, when white light crosses the boundary between air and glass, it can split up into the colours of the spectrum. Explain in terms of speed why light behaves like this. So, firstly, you need to understand that white light is made of 7 different colours, the colours of the spectrum, or the rainbow if you like, and they all travel at different speeds. So red travels the fastest, it has the longest wavelength and travels the fastest, and violet travels the slowest. The slower a wave travels, the more it refracts, or the more it changes direction due to refraction. So to answer this question, each colour has a different wavelength, so travel at different speeds, so refract different amounts. And that makes sense if you think about the velocity or wave speed equals frequency times wavelength formula. If they all have different wavelengths, for example, red has the largest wavelength, so there's an increase here, and the frequencies are the same, so the same number of waves are arriving at one point and then the next point, then it makes sense that the velocity will increase if it's traveling, if the wavelength increases, because wavelength times frequency is wave speed. So by increasing this, we're going to increase this. On the other way, if we slow things down, so if we decrease the wavelength, like in the case of violet, then multiplying it by frequency by a smaller number will lead to reduction velocity. So mathematically it makes sense as well. So each colour has a different wavelength, travels at different speeds, so refract different amounts. Next question. The following descriptions describe waves from different parts of the electromagnetic spectrum. Complete each description by adding the name of the wave. Use the name of each wave only once. Each description refers to a different part of the electromagnetic spectrum. This is actually a little bit trickier than it may initially seem. Firstly, remember the electromagnetic spectrum. So radioactive mice invade Venus using X-ray guns, radio, microwaves, infrared, visible light, UV, X-rays and gamma rays. And you can see that radio waves have the lowest frequency and the largest wavelength. Gamma rays are highest frequency and they have this very short wavelength. So the first one, used in cooking, used in short range communication, typical wavelength 900 nanometers. But this one says used in cooking as well, used in communication, typical wavelength 150 millimeters. So here we've got a much smaller wavelength. Here we've got a much larger wavelength because this says nanometers, not millimeters. So which two are used in cooking? Well, firstly, we have to look at these two. Microwave and infrared are the two used in cooking. This one uses is how we cook in, let's say, normal ovens through conduction, and this is how we cook in microwave ovens. So which one has the longer wavelength? Microwaves have the longer wavelength. So this one must be microwaves, this one must be infrared. So if we go down, infrared and microwaves. Then used in communication, produced by oscillations in electrical circuits, typical wavelength 150 meters. So communication could be microwaves or radio waves, but we've got very long wavelength, and also produced by oscillations in electrical circuits. So that's how antennae work. So radio waves cause electrical or induce electrical currents in antennae. So that should be radio waves. And finally, used in medical scanning, is emitted by the nucleus of an atom, typical wavelength 2 times 10 to the minus 3 nanometers. Now, you might instantly think, it's going to be X-rays, but the clue here is it's emitted by the nucleus of an atom. If you remember radioactive decay, sometimes the nucleus will emit gamma radiation, which can also be used in medical scanning. So actually, the final answer is gamma. So each one of these is a little bit trickier than it first seems, because you can see that it could almost be another one, but you have to pick out on a very key piece of information. So here it was the wavelength. Over here it was the fact that it had a very long wavelength, and this one it was the nucleus of an atom.